Great, so we're ready to do, what is this, 19C.1. We're going to divide it into two sections. And this is kinematics, which is the mathematics of things that move. And so suppose a car is moving. Suppose a car is traveling at 60 kilometers per hour for 15 minutes. How far does it travel? Well, we know it doesn't take calculus to figure that out. All we have to use is dirt. Distance equals rate times time, right? So it's traveling, the rate is 60 kilometers per hour, and it's traveling for 15 minutes, which means we have to convert that to hours. Easiest way is just to write that as a quarter. I'll just do that. It's quicker just to do it in our head instead of using dimensional analysis. So 15 minutes is a quarter of an hour. And then our units cancel and we get 60 divided by 4, which is 15 kilometers. Right? We already knew that. But is there a way that we could think of this graphically? And that's what we want to do, because we want to tie this in. We want to use calculus to tie it in. So if we want to think about it graphically, the way to set it up is to put time on the x-axis. And so in this case, that's hours. And the velocity on the, or in this case, I guess it would be speed, but usually velocity is going to go on the y-axis. So I'll just say velocity in kilometers per hour. And because the car is traveling at a constant rate of 60 kilometers per hour, that's going to be a horizontal line at 60. And for 15 minutes, so let's just say here's a quarter of an hour. And then if we were to find the area under the curve from 0 to a quarter of an hour, then that would actually end up giving us that total distance, because, and you can look at it with a unit analysis, so the total distance is the area under the curve, and in this case it's a rectangle, so it would be 60 kilometers per hour times the 1/4 hour, which obviously is what we just did. When you're finding, and then also we can look at this and we can write this as an integral. So the integral from 0 to 1/4 of the velocity with respect to time. And if you want to see, I could actually do the math probably pretty quickly here. The integral from 0 to 1/4, the velocity was a constant 60. So when you integrate that, you get 60t, and you're evaluating it from 0 to 1/4. And so again, you're going to have 60 times a quarter minus 60 times 0. And you get the same thing that we got earlier. So if you want to find the total distance and you have a rate of change, or in this case a velocity, you can integrate, find the area underneath the curve, underneath that velocity curve, or underneath the rate of change curve, and that'll give you your total amount of change. In this case, that's the total distance. Okay. So say the speed, so this is kind of a new example. Let's say the speed decreases at a constant rate and the car, so that I probably should have written this out ahead of time, so that the car initially traveling at 60 kilometers per hour, so that car initially going 60 kilometers per hour stops in 6 minutes, excuse me, which is or 1/10 of an hour. Find the distance traveled. And we want to do this with calculus, so we want to use a graph. Let's set it up with a graph. So again, the velocity is going to go on the y-axis, the time is going to go on the x. We'll keep the units kilometers per hour and hours. And initially it's going 60, so at time 0 it's going 60. And in 6 minutes, so 1/10 of an hour, it is stopping. So since it's stopping, the velocity is 0. And it's constant, so I can connect this with a line. And if we want to find the distance traveled, we'll just set up the integral 0 to 1/10 of the velocity. Now, I'm just going to write v of t dt. If you want to do the algebra, you could figure out the equation of that line, and you could put it there. But it's not necessary, because if you look at the graph, this is a geometric figure that we can quickly find the area of just using geometry. So let's just take the shortcut here and do base times the, so let's keep units on there, the base of the triangle times the height of the triangle times a half. So that's 60 over 20, which is 3. Hours cancel and you get 3 kilometers. So the calculus served us pretty well on that one. Okay, so in summary, if the velocity is positive, so above the x-axis, which we've had in both of the previous examples, so velocity has to be up here positive. Whoops, automatically put F there. It's funny. And say you've got time 1 and time 2. The total distance traveled is the integral from t1 to t2 of velocity with respect to time. But velocity has to be greater than 0 for that to happen. So, well, what if it is less than 0? Whoops, I should have drawn it like that. So let's do this as our v. t1, t2. And you can probably guess that if we want total distance, we want a positive value. And if v is below the x-axis, then we integrate, we're going to get a negative value. So in order to correct that, we would have to negate our integral. And if you have both, part of it is above and part of it is below, you have to break it into 2 integrals. So say it's like this, v of t. Whoops, that's not supposed to, that looks too much like the derivative of v. We don't want that. Say t1, t2, t3. And if you wanted to find the total distance, it would be the integral from t1 to t2 of v of t dt minus the integral from t2 to t3 of v of t dt. Since this second one's going to be negative, you have to negate it to get a positive distance. Okay. There is one more example, and it happens to be back here on the very front page. Right here. The time velocity graph for a train journey is illustrated in the graph alongside. Find the total distance traveled by the train. And this is very nice because they give you everything beautifully. The time is in hours, the velocity is in kilometers per hour. Just so happens everything's above the x-axis, so we simply need to find the areas. So you could do that on your own and see if you get the same thing I do. It's really up to you how you want to subdivide the areas. I'm looking at that. I'm seeing a triangle here. I'm seeing a nice rectangle there, a trapezoid there, a rectangle, and then a triangle. And so we're just going to find the areas of all those and see what we get. So the first one is a triangle, 1/2 the base. And I don't have to worry about units because I already looked at those and know that they're all going to cancel out to kilometers. The unit analysis is really helpful. When you're finding area, it's going to be the units on the y-axis times the units on the x-axis. And that's a good way to check to see if you have your integral set up too, like if it's a problem you're not sure about. Anyway, 1/2 base times height plus base times height plus the trapezoid. 1/2 the height, which is 0.1, times the sum of the bases, 50 plus 30, plus rectangle, base times height plus triangle, 1/2 base times height. And if you crunch all the numbers just to save time, I got 21 kilometers when I did it. And that concludes, I'm just kind of looking through and make sure I didn't miss anything. That's going to conclude section 19C.1.